Have you ever really thought about the journey electricity takes? I mean, every single second of every day. It's this incredible story of massive power, huge distances, and some really precise control. Okay, let's dive into this invisible world that powers pretty much everything we do.
It kind of seems like magic, doesn't it? One minute you've got power being generated miles and miles away, and the next, it's right there, charging the phone in your hand. So how on earth does it get from that power plant to your wall socket, safely and without just fizzling out? Well, that's the big question we're going to tackle today.
All right, so our journey starts right at the source. But here's the thing. This is not a simple A to B trip. Nope. It's more like a cross-country marathon through this massive, super intricate network we all know as the power grid. The whole thing happens in stages, kind of like a relay race for energy. It kicks off at the generating station. Then it gets handed off through a whole series of substations, grid, main, and city. And at each stop, the power gets changed just a little bit until it finally arrives right at your doorstep.
So right out of the gate at the power station, we're talking about 11,000 volts. That is a huge amount of electrical pressure. But believe it or not, for a journey across the country, it's actually not nearly enough.
You see, trying to send electricity over long distances is a bit like trying to send water through a really long, leaky hose. You're just going to lose a lot of it along the way. With electricity, that loss escapes as heat. So the really clever solution is to dramatically crank up the pressure, and that's the voltage.
And when I say dramatically, I mean a massive leap. At a grid substation, that voltage gets stepped up to a staggering 132,000 volts. This super high voltage is what lets the electricity just zip across the country on those big transmission lines with almost no power getting lost.
Now, of course, 132,000 volts would literally vaporize your TV. So as the power gets closer to towns and cities, it goes through more substations that do the opposite. They step down the voltage, making it safer and usable, until it hits a much more manageable 220 volts right at the power pole just outside your house.
So we've seen this epic journey, but to really get how it all works, we've got to get to know the basic forces at play. You can think of them as the three fundamental building blocks of all things electricity. Okay, this is honestly one of the best ways to get a feel for these concepts. Just imagine electricity in a wire is like water flowing through a pipe. The voltage is the pressure pushing the water. The current is how fast the water is flowing. And the resistance, well, that's anything that makes the pipe narrower and slows down that flow.
So let's look a little closer at voltage. It's measured in volts, and it's simply that electrical pressure. It's the push, the force that gets all those charges moving in the first place. No voltage, no flow. Simple as that.
And that flow itself, that's what we call current. We measure it in amperes, or just amps for short. It's basically a count of how much charge is zipping past a single point in the wire every second. So a higher amp rating means a stronger flow. And finally, we have resistance, which is measured in ohms. It's the opposition, that narrowing of the pipe. But here's the cool part. Resistance isn't the enemy. In fact, it's absolutely essential. This electrical friction is exactly what converts energy into useful work, like the heat and light you get from a light bulb's filament.
So we've got our three key players: voltage, current, and resistance. But how do they all relate to each other? Well, luckily for us, there's a beautifully simple rule that governs their relationship.
This relationship is all defined by Ohm's law. Now, it sounds a little technical, but all it's really saying is that if you increase the push, the voltage, you're going to get more flow, more current. It's a really simple, elegant rule that pretty much runs every circuit you can think of.
This relationship gives us this super simple but incredibly powerful formula. V equals I times R. So voltage is just the product of current and resistance. This one little equation is basically the key to understanding how all electrical circuits are designed and balanced.
Okay, so we've got the power to our home, and we understand the basic rules of the road. Now what? How is the wiring inside your house actually designed to make everything work together? Basically, there are two main ways to wire things up: in series or in parallel. In a series circuit, everything is on one single loop. You know those old-fashioned holiday lights, where if one bulb burns out, the whole string just dies? That's a series circuit. But in a parallel circuit, every device gets its very own branch. And that distinction is what makes a modern home actually work. Let me ask you a question just to make this super practical. Think about it for a sec. When a light bulb burns out in your kitchen, does your refrigerator suddenly shut off too?
Of course not. And that is all thanks to your home being wired in parallel. This absolutely brilliant design makes sure that every single outlet gets the full 220 volts and that each appliance can be turned on or off all on its own without breaking the circuit for everything else.
Now, with all of this power flowing through our walls, safety is, well, it's obviously the #1 priority. So, built right into our home electrical systems are a few silent guardians that are always on watch. Think of it like a safety team, and on the starting lineup, you've got a few key players. The classic fuse, its modern cousin, the miniature circuit breaker, or MCB, and the super important earth wire. Each one has a job to do to protect you and your home. The fuse is a true self-sacrificing hero. It's designed to be the weakest link in the chain on purpose. When the current surges to a dangerous level, this special little wire instantly melts, sacrificing itself to break the circuit and stop that dangerous flow before it can destroy your expensive stuff.
And what are they protecting you from? Well, two main dangers. The first is a short circuit. That's when damaged wires touch and create this super easy path for a massive, dangerous surge of current. And the second is overloading, which happens when you just plug in too many high-power things at once, trying to pull more current than your home's wiring can safely handle.
So there you have it. From a distant power plant through all those transformers and substations, governed by the simple elegance of Ohm's law, and protected by those little fuses and circuit breakers, this energy completes its incredible journey. It's this system of immense scale and amazing precision. Which kind of makes you wonder, doesn't it? What part of your world is it powering at this very second?